So myself, Dr. C.R. Kesavulu, Associate Professor, Department of Physics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I am going to discuss about the theoretical analysis for energy transfer parameter by using IH model. So in this study we are going to use the theoretical analysis for the energy transfer parameter by using the IH model is Inoue-Hirayama model. This is one of the important theoretical model from the laser glass. So last one previous session was discussed on the theoretical analysis for the Joule of light intensity parameters. We are Joule of light intensity parameter we are calculated from the optical observation spectra. We are calculated oscillator strength, Fx mean F calculated value, and the root mean square RMS deviation we are calculated from the observation spectra only. Joule of light intensity parameters omega 2, omega 4, omega 6 also calculated from the JO theory only, and relative properties such as radiative transition property AR, radiative lifetime, branching ratio, and stimulated emission relaxation. This also we are calculated from by using the radiative properties and oscillator strengths from the JO theory only. So these are the last session we discussed. So present session we are mainly focusing on the theoretical analysis for energy transfer parameter by using IH model. IH is nothing but Inoue-Hirayama model. By using Inoue-Hirayama model, we are calculating the energy transfer parameters. So first we need to study the luminescence lifetime and or decay lifetime. For example, we are taking the terbium triplet doped phosphide glasses. So Inoue-Hirayama model, what is the equation of the Inoue-Hirayama model? Next, energy transfer parameter value, that is Q, we are going to discussing, and donor acceptor interaction parameter CDA value we are discussing in the present study. These are focused in the theoretical analysis for the energy transfer parameters by using IH model. So first, luminescence decay time measurements. So here this is the decay lifetime or luminescence decay time for the 5D4 level, particularly in the terbium 3 plus doped glass. In terbium 3 plus 5D4 level, we are showing the all the lifetime measurements and shows the single exponential nature. That is, there is no energy transfer parameter. So in this case, in 5D4 level, in particular in the terbium 3 plus doped glasses, we are getting the 5D4 luminescence level is each and every lifetime measurements will be exhibit the single exponential nature. That means it exhibits single exponential nature means each and every peak there is no energy transfer parameter. We cannot, by using the IH model, we cannot fit this single exponential nature. Whenever we get in the non-exponential nature, that kind of luminescence decay times only we can use to fit the Inoue-Hirayama model. So by using this single exponential, we are unable to calculate the IH model. That is why you are showing here 5D4 level, it shows the completely single exponential nature. This is the luminescence decay analysis, very useful for the understanding the energy transfer mechanism and luminescence quenching behavior of the terbium 3 plus ions. This figure shows the decay curves for the 5D4 level for different terbium 3 ion concentrations obtained by monitoring the green emission. Here monitoring the green emission 540 nanometer, exciting with 376 nanometer. The decay curves exhibit single exponential nature for all the concentration of the studied terbium 3 plus doped glasses. So all the experimental lifetimes were determined the 2.94 to 2.2 milliseconds for the 1 mole constant weight percentage to 5 mole weight percent. This shows this all the terbium 3 plus concentration having the single exponential nature. There is no energy transfer parameter. We are unable to calculate the energy transfer parameter because there is no doesn't have any energy transfer. That means there is no quenching of the lifetime measurement. This is almost similar lifetime you are getting 2.94 to 2.2. There is a difference will be very less. That is why it does not exhibit the energy transfer parameter. That is why this is shows the completely single exponential nature. So we are unable to study the IH model fitting for the 5D4 energy level of the terbium 3 plus ions. Now we are going for the study the 5D3 level. This 5D3 level shows the completely non-exponential nature. If you see the concentration from the 1 mole concentration to 5 mole terbium concentration of the 5D3 level. 5D4 level it exhibit completely single exponential nature. But in 5D3 level exhibit the completely non-exponential decay curves. This well fitted to by using this formula. This tau experimental value we are calculating the integral Ti of t dt to integral of I t dt. This is the decay curve for the 5D3 level of the different terbium 3 ion concentration in the phosphide glasses. The incident diagram shows the variation of the energy transfer parameter Q with the terbium ion concentration of ions per centimeter cube. This incident diagram shows the terbium ion concentration versus energy transfer parameter. So increase the concentration, the energy transfer parameter also increasing. That is, we can observe this behavior in the non-exponential nature of the lifetime measurements only. Particularly in the turbulent 3 plus science, 5D4 level shows the single exponential. So that is doesn't shows the any energy transfer parameter. But in the case of 5D3 level of the turbulent 3 plus science shows the non-exponential nature. By using non-exponential nature only, we are going to study the IH model. IH fit we can use to non-exponential nature of the decay times only. We can fit the IH model. So that is Inocuity-Hirayama model is the IH model. This is the equation for the IH model. I of t equal I naught, that is intensity of lower energy level, exponential of the minus t by tau naught. Tau naught is the luminescence decay time of the, particularly in the case of terbium 3%. Q is the energy transfer parameter, and t and this correspondence tau naught. 3 by s, this is important. 3 by s, s is the mainly, that is the s indicates the dipole parameter, dipole quadrupole. This is the important parameter to study the energy transfer parameter. Since the lifetime for the 5D3 level is found to be decreased with the increase in the terbium 3 plus concentration, the quenching of lifetime and its non-exponential nature could be due to the increased energy transfer process through cross relaxation between the terbium 3 plus ions of the ground state and excited state of the terbium 3 plus ions. In order to find out the nature of the energy transfer process, the decay curves are well fitted in the Inocuity-Hirayama model, that is IH model. By using this reference number 2, we are calculating the IH model, that is equation of the IH model equation. This I is the intensity given by T is the time of the after excitation, tau naught is the intrinsic decay time of the luminescence time of the donors in the absence of acceptors, tau 0 is the radiative or lifetime of the respective case of the terbium 3 plus ions. By using this formula, we are calculating the energy transfer parameter Q. Q is the energy transfer parameter, that is a formula Q equal 4 by 3 is gamma 1 minus 3 by S N naught R naught cubed. See here, Q depends on the number of S is the gamma function. S is and the gamma function of psi x, which is equal to, if S equal to 6, we are using S equal to 6, S equal to 8, and S equal to 10. These are the three important energy transfer parameters. One is S equal to 6, S equal to 8, S equal to 10. One, this equation well fitted to S equal to 6 means that shows the dipole nature. If you are getting 1.77 is the dipole nature for S equal to 6. That equation is well fitted to S equal to 8 means that value will be 1.43, that shows the dipole quadrupole nature. If that S equal to 10 equation is well fitted with S equal to 10 means that value is 1.30, that is well fitted with the quadrupole and quadrupole interaction between the energy transfer parameter. So this Q value shows the using of the gamma function. This Q depends on the number of S and gamma function psi x. By using that formula only, we are calculating the Q values. By using this formula, we are calculating the energy transfer parameter of the, by using Inocuity-Hirayama model. See, N naught is the acceptor concentration, that is the terbium 3 plus ion concentration, which is almost equal to the, terbium 3 plus ion. By using here terbium 3 plus ion concentration of the N naught is the acceptor concentration, which is almost equal to the total concentration of rare earth ions. R naught is the critical transfer distance defined as the donor acceptor separation, for which our rate of energy transfer between donor and acceptor is equal to the rate of intensity decay time tau naught. This 5D3 luminescence decay is in the paper well discussed and described in this energy transfer parameters. By using this formula only, we are calculating the energy transfer parameter, that is in the case of S equal 6 and S equal 8 and S equal 10. If S equal 6 is well fitted means that shows the dipole interaction. If S equal 8 means dipole and quadrupole interaction. If S equal 10 means quadrupole interaction between the terbium 3 plus ions. That is shows the energy transfer parameter. Next, fourth one is the donor acceptor interaction parameter CDA. The donor interaction parameter CDA is related to R naught value. So R naught is the interelectronic distance R naught, and the CDA is the donor acceptor interaction parameter. That is the donor with terbium 3 plus 2, terbium 3 plus ions. Terbium 3 plus 2, terbium ground state, terbium 3 plus ion to excited state, terbium 3 plus ions. What is the donor to acceptor interaction? How much CDA value is changing from the increase in the concentration of the terbium 3 plus ions. See the decay curves of the phosphate glasses well fitted to IH model. The S equals 6 in the present case, S equals 6 in the indicator. That means in this lifetime, here this completely each and every non-negative exponential nature will be well fitted to S equals 6. This red line shows the this completely well fitted to IH model S equals 6. That is why it shows the dipole nature. So that is only here studying. This is the, so this non-exponential decay also, this S equals 6 indicates the dipole interaction between the terbium 3 plus ions. This analysis of non-exponential decay curves yields the values of Q that increases approximately linearly with turbine triples ion constant. That is here showing here in this diagram. See, turbine triples ion concentration increases, energy transfer parameter Q also linearly increases. That is shows the S equals 6 is the energy transfer parameter is shows the dipole-dipole interaction. That is a dipole-dipole interaction only you are taking the energy transfer parameter, that is non-reactive relaxation. That is you are calculating the by using the next CDA. This is donor acceptor interaction parameter. We are calculating by using the CDR not by donor. By using these values, we are calculating the donor acceptor interaction parameters. In this present study, by using that values, we are calculating the different turbine triples concentration of the this values, the tau experimental n naught values of the each and every terbium concentration values, and Q is the energy transfer parameter for the lower concentration source the 0.4 to 2.6. That is increasing the concentration energy transfer parameter also linearly increasing from 0.44 to 2.64. And R naught value also almost constant 10.2, 10.5, 10.7, 10, 10.8. But CDA value 1.2, 1.4, 1.5, 1.0, 1.6 for particularly turbine frequency. But here in the case, this Q value is very important. We are studying the IH model is mainly used to study for the energy transfer parameter. So Q value increases. Increasing means it shows the while increasing the concentration of the terbium triple science, energy transfer parameter also increasing from lower concentration to higher concentration. Here we are using the IH model equation. This is the I of t equal I naught, and the Q value is a formula. This three formulas is belongs to the IH model. That is Inoue-Kitty Hirayama model. By using this model, this is Japan scientists, they discussed the theoretical model to study the energy transfer parameter of the, particularly in the case of terbium triplet ions, by which luminescence decay time shows the non-exponential nature. Single exponential nature, we are unable to fit the Inoue-Kitty Hirayama model. Whenever this luminescence lifetimes is shows the non-exponential nature, at that time we can study the Inoue-Kitty Hirayama model. Using the Inoue-Kitty model, we can study the energy transfer parameters. So in our terbium 3 plus 5D3 luminescence lifetime, we cannot get the energy transfer parameters. But in the 5D4, 5D3 level, we are observing the non-negative, that means a non-exponential nature. At the same time, you are getting the energy transfer parameters of the Q value and R naught and CDA values. So these are the references used in the present study of the theoretical analysis for energy transfer parameter by using the IH model. So by using the lifetime, experimental lifetime, tau experimental we are calculating by using this reference, the Inoue-Kitty Hirayama. By using this reference, we are calculating the IH model. This study values is mainly presented in this paper, that is Journal of Luminescence, published in the 2015. So these are the important reference, particularly focused in the theoretical analysis for energy transfer parameter by using IH model. Thank you. Thank you once again.
Like, share and subscribe. Hit the bell icon for more updates.